Fine. Let's start. At the center of our galaxy, 26,000 light-years away, sits a black hole called Sagittarius A-star. It weighs 4 million times what our Sun weighs. It is the gravitational anchor of the entire Milky Way. Every star in the galaxy, including ours, orbits around it, slowly, obediently, over hundreds of millions of years. For a long time, we thought it was alone. The evidence is starting to suggest it wasn't. Number 10. The stars that should not exist. Here is a simple rule of astrophysics. The closer you get to a supermassive black hole, the more violent the environment becomes. The tidal forces, the difference in gravity between one side of an object and the other, become so extreme that gas clouds get shredded before they can collapse, before they can cool, before they can do the one thing gas clouds in space eventually do, which is form stars. So naturally, within a fraction of a parsec of Sagittarius A-star, there are stars, young ones, massive ones, Wolf-Rayet stars, and OB supergiants, the kind of stars that burn so hot and bright they only live for a few million years, which means they formed recently, which means they formed right there, in the one place in the galaxy where that should be physically impossible. Astronomers gave this problem a name: the paradox of youth. That's not a poetic nickname. That's the actual term in the literature. The stars are too young to have migrated there from somewhere safer, and the environment is too hostile for them to have formed where they stand. The leading early explanation, published in 2003 by Brad Hansen at UCLA and Milos Milosavljevic at Caltech, was direct to the point of being almost uncomfortable. Their paper was titled, "With Remarkable Candor for Academic Science," the need for a second black hole at the galactic center. Not possible evidence for, not tentative indications of. The need, as in, we looked at the data, and something has to be there. Their proposal was that an intermediate mass black hole, somewhere between 1,000 and 10,000 solar masses, had acted as a gravitational tugboat, dragging a star cluster inward from a safer distance, close enough that the tidal field of Sagittarius A-star could peel the stars off and scatter them into the orbits we observe today. There are other explanations. There's a competing model involving a gas disk that formed stars in situ a few million years ago before vanishing. That model is currently the mainstream preference. But here's the thing. It doesn't cleanly explain all the orbits. It handles the clockwise disk of young stars reasonably well. The innermost population, the S-stars, with their chaotic, randomly tilted, highly elliptical orbits, still a problem. The paradox of youth is 20+ years old. It is still technically open. Something put those stars there. We're still arguing about what. Number 9. The star that escaped at 6 million kilometers per hour. In 2019, an astronomer named Sergei Koposov was running a survey of stellar streams at the edges of the Milky Way, essentially mapping the debris trails left by smaller galaxies our galaxy has absorbed. It is painstaking, unglamorous work. And then, buried in the data, he found something that had no business being there. A star, moving at 1,755 kilometers per second relative to the galactic center. For comparison, our Sun moves through its orbit around the Milky Way at about 220 kilometers per second. The new star was moving at 8 times that, fast enough to escape the galaxy entirely, which it is currently doing. It will never come back. They called it S5 HVS1, the fastest main sequence star ever recorded. Using the Gaia satellite's precision astrometry, the team traced its path backward in time, and it pointed, without ambiguity, directly at Sagittarius A-star. The black hole had flung it outward approximately 4.8 million years ago. The mechanism is called the Hills mechanism, named for astronomer Jack Hills, who proposed it in 1988. The basic idea: a binary star system wanders too close to the black hole. The black hole's gravity tears the pair apart, capturing one star into a tight orbit and catapulting the other outward at extreme speed. The ejected star essentially absorbs the orbital energy of its former partner. It becomes a bullet, and S5HVS1 is a very fast bullet, nearly twice as fast as any other hypervelocity star confidently attributed to Sagittarius A-star. The discovery paper noted this discrepancy. The authors were careful about it. They raised the possibility that either the ejection mechanism was different in this case, or the velocity distribution of these stars has not been constant over time. What they did not rule out, what no one has ruled out, is that something else was involved. Something else at the center that day, 4.8 million years ago, that added an extra gravitational kick to the catapult. A star that should be traveling at 500 kilometers per second is traveling at nearly 4 times that. That extra energy had to come from somewhere. It left, and it took its secrets with it. Number 8. Messier's Ghost. In 1778, Charles Messier was cataloging fuzzy objects in the sky. His goal was to document things that might be mistaken for comets. One of the objects he recorded was a dense cluster of stars near the constellation Sagittarius. He labeled it Messier 54. He assumed, reasonably, that it was part of the Milky Way. He was wrong. In 1994, Rodrigo Ibada and colleagues discovered the Sagittarius dwarf elliptical galaxy, a small galaxy that has been, for an unknown number of orbits, slowly dying inside the gravitational grip of the Milky Way. Our galaxy has been peeling it apart, pass by pass, orbit by orbit. The outer stars are gone. The disk is gone. What remains is a core, a stream of stripped stars wrapping around the Milky Way like a scar, and, sitting at the very center of what's left, Messier 54. Messier 54 is not a Milky Way globular cluster. It is the nucleus of a galaxy we are currently eating. It sat in the most famous astronomical catalog in history for 216 years under a false identity. It was extragalactic the entire time. And the Sagittarius dwarf is still here. It's on its 3rd or 4th pass through the Milky Way's disk. Each time, the tidal forces strip away more of it. Each time, Messier 54 gets pulled a little closer to the center. The dwarf galaxy's black hole, evidence for a mass of around 10,000 solar masses, has been reported at M54's core, is being physically escorted over the course of millions of years towards Sagittarius A-star. This is not a future hypothetical. It is happening. In slow motion, over timescales we can't perceive, a second galaxy's nucleus is being delivered to our own. Messier filed it. 2 centuries later, we found out what it actually was. Number 7. The largest invisible structure in the Milky Way. In 2010, NASA's Fermi Gamma Ray Space Telescope found something that, by all rights, someone should have seen before. 2 enormous bubbles of gamma ray emission, one above and one below the galactic center, each stretching approximately 26,000 light-years into the halo. Together, they span the equivalent of a third of the sky. Perfectly symmetric. Perfectly centered on Sagittarius A-star. No one had seen them before because gamma rays require a dedicated space telescope to detect. Invisible light, radio waves, infrared, nothing. In gamma rays, suddenly, the largest coherent structure in the entire galaxy. The question was obvious. What made them? The energy budget is extraordinary. Filling 2 structures that size requires the equivalent of roughly 100,000 supernova explosions. Something pumped an enormous amount of energy into the galactic halo. And it did so recently enough in cosmic terms that the bubbles haven't dispersed yet. Best estimates put the event somewhere between 1 and 3 million years ago. One leading explanation requires Sagittarius A-star to have been an active galactic nucleus, essentially a quasar in miniature, approximately 10 billion times brighter than it is today, blasting twin jets of energy out along its rotation axis for around 100,000 years. Here's the thing. Some of those models tie the timing of that outburst not to a random accretion event, but to the final spiral of a companion object. A second black hole, losing orbital energy, feeding material onto Sagittarius A-star as it spiraled inward during its last few million years. The gravitational energy of that inspiral, converted to radiation, converted to jets, inflated the bubbles. The timing fits. The energy fits. We don't know if that's what happened. But something, a few million years ago, woke Sagittarius A-star up. And whatever it was, it left a mark so large it took us until 2010 to have the instruments to see it. Number 6. Omega Centauri, the black hole that's been here the whole time. You can see Omega Centauri with the naked eye from the southern hemisphere. It looks like a smudged star, a fuzzy patch near the constellation Centaurus. It is actually a ball of approximately 10 million stars, 17,000 light-years away, the largest and brightest globular cluster in the Milky Way. Except it isn't a globular cluster. The signs have been there for decades. Omega Centauri has multiple distinct stellar populations, different ages, different chemical compositions, which is not what you find in a true globular cluster. It has an unusually large mass. It has a strange orbit. The consensus in the field, growing stronger over the past 2 decades, is that Omega Centauri is the stripped nucleus of a dwarf galaxy that the Milky Way absorbed billions of years ago. The outer stars of that galaxy are long gone. What we see today is just the core, the most gravitationally bound part, the last thing to let go. And in June 2024, a team from the Max Planck Institute for Astronomy published something in the journal Nature. They had found 7 stars in the innermost 3 arcseconds of Omega Centauri, a region about 1/10 of a light-year across, moving faster than the cluster's overall mass can explain. The only clean fit, a central black hole of at least 8,200 solar masses, one of roughly 10 confirmed intermediate mass black holes in the known universe, orbiting inside our own galaxy, 17,000 light-years away. But here's what makes this stranger still. Models of how galaxies assemble suggest that between 2 and 6 other stripped galactic nuclei, objects like Omega Centauri, remnant cores of consumed galaxies, are currently orbiting inside the Milky Way's halo. Each one a former galaxy, each one potentially carrying its own black hole, moving through our galaxy right now, undetected. We keep talking about whether the Milky Way has a second black hole. It may have several. Number 5. The stars arriving from the wrong direction. In 2025, a team at the Harvard-Smithsonian Center for Astrophysics published an extraordinary piece of detective work. Astronomer Jiwon Jesse Han and colleagues had been tracing the origins of hypervelocity stars, those stars moving fast enough to escape the galaxy entirely. The standard assumption was that essentially all of them came from Sagittarius A-star via the Hills mechanism. They took 21 of these stars and used the Gaia satellite's precision measurements to reconstruct their 3-dimensional trajectories. Not just where they were going, where they came from. 7 traced back to the galactic center. Expected, 9 did not. 9 of them, more than half of the confidently classified sample, traced back to the center of the Large Magellanic Cloud, a dwarf galaxy sitting about 160,000 light-years away, a satellite galaxy of the Milky Way, visible as a smudge of light in the southern sky, observed by Magellan sailors in the 1500s, studied extensively for centuries. The Large Magellanic Cloud does not have a known active galactic nucleus. No one had confirmed a supermassive black hole there. But the Hills mechanism only works one way. To fling a star at those speeds, you need a supermassive black hole tearing apart a binary system. There is no other known mechanism. So Han's team did something elegant. They built a model. If a supermassive black hole of around 600,000 solar masses existed at the center of the Large Magellanic Cloud, moving the way the LMC moves around the Milky Way, it would produce a specific overdensity of hypervelocity stars in a particular region of our sky. The stars ejected along the direction of the LMC's motion would get an extra speed boost. They'd cluster. The model made a precise prediction. Then they checked, and the cluster was there. It is astounding to realize that we have another supermassive black hole just down the block, cosmically speaking, Hahn said in the announcement. Black holes are so stealthy that this one has been practically under our noses the whole time. The Large Magellanic Cloud is on a slow collision course with the Milky Way. In approximately 2 billion years, it will merge with us. And when it does, its black hole, 600,000 solar masses of it, will begin its journey towards Sagittarius A-star. We've been watching it from the backyard for 500 years. We just found out what it's carrying. Number 4. The Goalkeeper. Here is a strange fact about hypervelocity stars in the Milky Way. Every single one that's been observed moves at less than 700 kilometers per second. Not one has been found above that speed. This seems unremarkable until you run the physics. The Hill's mechanism, binary stars torn apart near a black hole, doesn't produce a clean upper limit. Depending on the initial orbital parameters of the binary, you should get a distribution of ejection speeds. Roughly half of all hypervelocity stars, by the models, should be moving faster than 700 kilometers per second. Possibly much faster. None of them are. In 2025, astronomer Chunyang Chao of Peking University and colleagues published a paper in the astrophysical journal Letters laying out two simultaneous anomalies in the hypervelocity star population. First, the speed cap. Second, the missing companions. When Sagittarius A-star tears a binary apart, one star gets ejected and the other gets captured, dropped into a tight orbit around the black hole. If we look at the stars orbiting close to Sagittarius A-star today, we should find some of those captured companions. Their binary partners were thrown outward 50 to 250 million years ago. The companions should still be there. They're not. Both problems, the speed cap and the missing companions, disappear if you add a second black hole to the galactic center. An intermediate mass object, roughly 13,000 solar masses, orbiting alongside Sagittarius A-star. Chao's team calls it, informally, a goalkeeper, an object that intercepted stellar binaries approaching the galactic center and deflected them before they could get close enough to Sagittarius A-star to be fully disrupted. Some binaries got kicked out whole. Some companions got redirected. The speed distribution gets capped because the goalkeeper was absorbing or deflecting the highest energy encounters. Their model places the final merger of the two black holes at approximately 10 million years ago. To give you a sense of that timescale, 10 million years ago, our genus, Homo, did not yet exist. Our hominid ancestors were early Australopithecines. The universe had a supermassive black hole merger at the center of our galaxy, and the most advanced beings on Earth watching it would have been bipedal apes who had recently figured out how to walk upright. There's one more detail. When two black holes of unequal mass merge, the emission of gravitational waves isn't perfectly symmetric. The surviving black hole gets a kick, a recoil, in the direction opposite to the loudest burst of waves. Chao's team suggests this recoil may account for a very slight, very precise drift in Sagittarius A-star's current position relative to the true dynamical center of the galaxy. A wobble. Fading, but potentially still measurable. The goalkeeper is gone, but the cord is still rocking slightly where it stood. Number 3. The cluster at the door. There is a star cluster called IRS-13. You've probably never heard of it. It sits 0.1 light years from Sagittarius A-star, which means that in astronomical terms, it is essentially on the doorstep. 0.1 light years. For reference, the nearest star to our sun is 4.2 light years away. IRS-13 is 42 times closer to the galactic center's black hole than we are to our nearest stellar neighbor. It was first observed as what appeared to be a single unusually massive star. Then, with better instrumentation, a small group of stars. Then, a denser cluster. Observations published in 2024 by Florian Peisker and colleagues at the University of Cologne using the Very Large Telescope, the ALMA radio array, and NASA's Chandra X-ray Observatory found that IRS-13 contains at least 70 individual objects. It is the most densely packed stellar region anywhere in the Milky Way. And then there's what's at the center of it. The stars in IRS-13 don't move randomly. They move in an unexpectedly orderly pattern, structured, coherent, as if they're orbiting something, and that something isn't visible. Chandra detected characteristic X-ray emission from the suspected location. ALMA detected ionized gas rotating at several hundred kilometers per second. Not drifting, spinning, in a ring, around a point that emits no light. There are, as of 2024, approximately 10 confirmed intermediate mass black holes in the entire known universe. Finding one anywhere is a significant event. Finding one 0.1 light-years from Sagittarius A-star, practically adjacent, in cosmic terms, is extraordinary. Here's the thing. IRS-13 has been studied for about 20 years. For 20 years, increasingly powerful instruments have been pointed at it. Each time, it turned out to be something more complex, more strange, more structured than the previous observation suggested. Something invisible at its center has been there the entire time, quietly holding 70 stellar objects in formation, while the most powerful telescopes in human history examined it, and each time thought they'd finally understood it. They had not. The most watched piece of sky in astrophysics was hiding something. It may still be. Number 2. The spin that remembers. In April 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A-star. It was a triumph. A ring of hot glowing gas around a dark central void, 27,000 light-years away, captured by a planet-sized array of synchronized radio telescopes. We had seen our galaxy's central black hole, directly, for the first time. What was celebrated that day was the image itself. What was not the headline, what came later, in September 2024, in a paper by UNLV astrophysicists Yihan Wang and Bing Zhang, published in the journal Nature Astronomy, was what that image contained beyond the picture. Sagittarius A-star spins. All black holes spin, but the spin axis of Sagittarius A-star is significantly misaligned relative to the rotational plane of the Milky Way galaxy. The black hole's spin is tilted, dramatically, and it's spinning fast, near the upper end of what's physically possible. Wang and Zhang modeled every plausible growth scenario they could construct. Slow accretion from ambient gas, accretion from misaligned gas clouds over time, various combinations. None of them produced the observed spin cleanly. Only one scenario reproduced it. A merger. A 4-to-1 mass ratio merger. Sagittarius A-star consuming a black hole approximately 1/4 its own mass. At a highly inclined orbital angle, somewhere between 145 and 180 degrees off-plane. The kind of collision that would come in steep, from above or below, slamming into the galactic plane at an angle. The kind that would torque the surviving black hole's spin axis hard to the side and lock it there. They placed the timing of this merger at approximately 9 billion years ago, coinciding with a galaxy collision we already know happened. The Milky Way's absorption of the Gaia Enceladus dwarf galaxy, a galaxy that added roughly 50 billion solar masses to our own. Here's what that means. The image we celebrated in 2022, the first photograph of our galaxy's heart, was not just a picture of a black hole. It was a photograph of a black hole that carries, encoded in its spin, the physical memory of a collision with a second, supermassive black hole. The second black hole isn't hiding anymore. It was consumed. It became part of Sagittarius A-star 9 billion years ago. What we see at the center of our galaxy today is the combined remnant, the merger product. The scar is the spin, the most famous photograph in recent astronomy history. And somewhere in the physics of that glowing ring, if you know where to look, you can read the fingerprint of a black hole that no longer exists. Number 1. The cartography satellite that found a ghost. In 2013, the European Space Agency launched a satellite called Gaia. Its mission was precise and unglamorous. Measure the position, distance, and motion of as many stars as possible. Make a map. The most detailed three-dimensional map of the Milky Way ever constructed. Gaia was not built to discover lost galaxies. It was built to count stars and record coordinates. And then the data came in. In 2018, astronomers analyzing Gaia's first major data release noticed something in the velocities of stars in the Milky Way's inner halo. A population of stars moving in a pattern inconsistent with having formed in the Milky Way. Their orbits were wrong, highly elliptical, streaming inward, chemically distinct. The pattern pointed to a single origin, a galaxy that had collided with the young Milky Way somewhere between 8 and 10 billion years ago. A galaxy that had been completely consumed, no trace visible in the sky, just its ghosts, moving through our stars with foreign orbits, chemically tagged from their birthplace. They named it Gaia Enceladus, also known as the Gaia sausage, for the elongated shape of its velocity distribution. It was enormous. A 4-to-1 mass ratio merger. The Milky Way 4 times heavier, Gaia Enceladus 1, that added at least 50 billion solar masses to our galaxy, including at least 8 globular clusters. The merger reshaped the Milky Way's disk. It triggered waves of star formation. It was, arguably, the defining catastrophic event of our galaxy's history. And almost certainly, Gaia Enceladus had a black hole. Nearly every galaxy of that mass does. We don't know its precise mass. The models from Wang and Zhang at UNLV and Chow and colleagues at Peking University both converge on something in the range of 10,000 to 15,000 solar masses. An intermediate mass black hole, the nucleus of a galaxy that no longer exists. That black hole entered the Milky Way 9 billion years ago. It took time, billions of years, for dynamical friction and gravitational interactions to drag it toward the center. But eventually, the models say, it arrived. It fell into orbit around Sagittarius A-star. And then, slowly, that orbit decayed too. The two black holes spiraled closer and closer until approximately 10 million years ago, when they merged. 10 million years. The sun was already 4.5 billion years old. Earth was already 4.5 billion years old. The oceans existed. Continents existed. Life had been on this planet for nearly 4 billion years. And at the center of our galaxy, two black holes, one 4 million solar masses, one a fraction of that, completed a death spiral and became one. When that happened, they released an enormous burst of gravitational waves, ripples in the fabric of space-time that travel outward at the speed of light in all directions, forever. That burst left our galaxy 10 million years ago. It is currently somewhere between 10 and 11 million light-years away from us, spreading outward through the Virgo supercluster, carrying information about what just happened at the Milky Way's center. We will never detect it. It is too far away, too diffuse, too ancient. The Laser Interferometer Space Antenna, LISA, 3 spacecraft in a triangular formation, 2.5 million kilometers across, planned for launch in 2035, is the instrument we're building to detect events like this. It will be sensitive to exactly the kind of gravitational wave signal that merger produced. But ours is gone. LISA will study mergers in other galaxies. It will, if everything works, confirm that this kind of event happens, and how often, and at what mass ratios. And in doing so, It will either support or undermine every model we've built around what happened at our own center. Here's the thing that sits with me about all of this. The evidence for a second black hole in the Milky Way, the paradox of youth, the missing hypervelocity star companions, the speed cap, the tilted spin of Sagittarius A-star, the overdensity of stars arriving from the Large Magellanic Cloud, the dense star cluster at the Galactic Center's doorstep, none of it is direct. There is no photograph of a second black hole. There is no gravitational wave detection of our merger. There is no smoking gun. There is only inference, pattern recognition, the shape of what's absent. What we have is a galaxy that, when you look at it carefully enough, seems to be telling a story about a collision that happened 9 billion years ago, an inspiral that took billions of years, and a merger that happened 10 million years ago and sent a burst of gravitational waves outward into the universe carrying a message no instrument will ever catch. If the models are right, that's one merger, one detected ghost galaxy, one confirmed event. But Gaia also found evidence for at least 5 or 6 other past merger events in the Milky Way's history, each at different epochs, each involving a galaxy that no longer exists. If each of those galaxies had a central black hole, and statistically, many of them should have, then the question isn't whether the Milky Way has ever had a second supermassive black hole. The question is how many times it's happened, and how many of those mergers will ever have the evidence to reconstruct. We built an instrument to map the positions of stars. It found a dead galaxy. The dead galaxy had a black hole. The black hole fell into our center and became part of ours. And the only reason we know any of this is because a spacecraft noticed that certain stars were moving slightly wrong. The galaxy doesn't announce its history. It just carries it, quietly, in the spin of a black hole and the trajectories of stars, waiting, apparently, for someone to build a good enough ruler. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.